today's lecture, I will essentially be talking about the basic postulates of quantum mechanics. Postulates are a set of hypotheses, and then there is a theory which is essentially these postulates together with a mathematical framework which makes predictions which are supposed to be experimentally verifiable. The theory is not meant to explain the postulates, but given the postulates and the mathematical framework, you make theoretical predictions based on these postulates and compare with experiments the consequences of these predictions. Now, if the experimental results agree with the theoretical predictions, in a sense it is an indirect test of the postulates. So, quantum mechanics too works on a set of basic postulates. Several of these postulates have been already told to you by way of examples. The two-dimensional linear vector space illustrates these postulates quite well, as I will explain to you right away. So, the first postulate it says that every physically observable quantity is represented by a Hermitian operator. If you wish to give matrix representations to operators, this would be a Hermitian matrix. The experimentally measured values of the observable can only be the eigenvalues of the operator corresponding to that observable. So, for instance, in the familiar example of the two-level atom, the Hermitian operators that we thought up were s squared and sz. So too with the three-level atom. These are Hermitian operators, and we had matrix representation for these operators. In the case of the two-level atom, they were 2 by 2 matrices, Hermitian matrices, and in the case of the three-level atom, they were 3 by 3 Hermitian matrices. So, spin and the third component of spin, if you thought about it in terms of the spin doublet, which could be the electron or the proton or the neutron. In the case of the 2 and 3 level atomic systems, it would be just s squared and sz, which satisfied the algebra s squared is equal to sx squared plus sy squared plus sz squared. and Sz satisfied along with Sx and Sy, the Lie algebra the experimentally measured values of these observables can only be the eigenvalues of the operators corresponding to the observables. And Hermitian operators are selected because Hermitian matrices have real eigenvalues and all measurable quantities will have to be real quantities. So, right away it is good to see why Hermitian matrices have real eigenvalues. A Hermitian matrix has this property that H is equal to H dagger. Dagger would just mean interchange rows and columns and take the complex conjugate of every element in the matrix. I give you an eigenvalue equation, H psi is equal to A psi, where A is the eigenvalue and psi is the corresponding eigenvector. Clearly, in the Dirac notation, if I take the dagger, the ket would become the bra and the number would simply be replaced by its complex conjugate, but H dagger is equal to H. So, now I could well find psi H psi. H psi is a state because H is an operator that acted on psi to produce a new state H psi, and we are trying to find the inner product of psi with H psi. This quantity clearly from this equation is psi A psi, but A is a number and can be pulled out. So, you have the first equation, psi H psi is A inner product of psi with itself. That is the first equation. Well, you could have done that with this. You could have started with psi H and you could have had a psi on this side. That would have given me an A star psi psi, and this is my second equation. But since both quantities are the same, A must be equal to A star. In other words, the eigenvalue of the Hermitian matrix is real, and that is true for all eigenvalues. So, the set of eigenvalues of Hermitian matrices are real, and therefore, the experimentally measured values of the observable can only be the eigenvalues of the Hermitian operator corresponding to that observable. We also assume that the Hermitian operator is a bounded operator. The concept of a bounded operator really needs explanation only when we deal with infinite dimensional spaces. And since up to now I have only spoken about finite dimensional vector spaces, all finite dimensional vector spaces have this property that the operators are anyway bounded operators. The concept of boundedness of an operator is intimately linked with the concept of continuity, and both of them are best explained in the framework of infinite dimensional linear vector spaces, which I will do in a subsequent lecture. So, for the moment, these examples, the 2 and the 3 level atomic systems, really have only bounded operators as relevant operators. Having said that, in general, there is no need to imagine that all the eigenvalues of the Hermitian matrix should be a continuous set. In general, they could be discrete eigenvalues, and that is precisely why the observable could be quantized with discrete values, in contrast to a classical system where the measurement outcome could take a continuous set of values. Here, for instance, in the familiar example of the 2 and 3 level atom, equivalently the spin doublet, this was certainly true that S squared acting on psi was S into S plus 1 h cross squared psi, and Sz on psi was m h cross psi. In the case of the two-level atom, S was half and Sz, m could take values minus half or plus half. And therefore, I defined for you in a previous lecture two basis states labeled by the S and m values, and the states were half half and half minus half. It was on the basis of this, you will recall that in passing I mentioned fermions and bosons. Fermions have half integer spin, that means S can take values half, 3/2 and so on, and bosons have integer spin, which means S can take values 0, 1, 2, 3 and so on. While Hermitian operators are certainly the only operators that can be used to represent physically measurable objects, it is also true that other operators have their own importance in quantum mechanics. For instance, we have already seen the operators S plus and S minus. We have seen unitary operators. An example would be e to the I theta Sz, which I spoke about in the last lecture. This is unitary because that is Hermitian, and this is exponential I times a Hermitian operator. Talking of eigenvalues, it is good to digress at this point and see in general what kind of eigenvalues a unitary operator can have. So, if U is a unitary operator, this is an example, and if this is the eigenvalue equation, correspondingly I can take the dagger and get this equation. A unitary operator satisfies this, and therefore I can find the inner product of this bra with this ket. This is a ket, and that is the bra vector corresponding to that ket vector. But this object is simply mod A squared psi psi, because U dagger U is identity. And if initially psi has been normalized to unity, it is clear that mod A squared is equal to 1. So, the eigenvalues of a unitary operator are complex numbers whose modulus is unity. We also have non-Hermitian operators in quantum mechanics which do important jobs, as for instance S plus and S minus. They were the raising and lowering operators. S minus was a lowering operator. In the context of the atomic system, because S plus on the ground state of the atom took it to the excited state, and S minus on the excited state of the atom gave us the ground state. We can easily find out the physical significance of the coefficients here. If you go back to the two-level atom problem, you will see that S plus was defined as H cross Eg. Let us recall that these were the two levels, and S plus acting on G gave me 1 H cross E, and S minus acting on E gave me 1 H cross G. S minus being the dagger of S plus. Now, in general, because S plus is the raising operator, it acts on the state given by labels S comma m, takes it to the state S comma m plus 1 with a coefficient which is S minus m times S plus m plus 1 H cross. Now, this is a general relation and we will derive this in greater detail later, and therefore, S plus in the case of the spin doublet or the two level atom would act on the state half minus half and give us 1 H cross as the coefficient and take it to the state half half. Now, similarly, S minus acts on a state given by the labels S comma m, takes it to the state S m minus 1 with a coefficient which is root of S plus m times S minus m plus 1. And therefore, in our example, S minus acting on the state half half will take it to this coefficient which really turns out to be 1 H cross times S comma m minus 1, which is half minus half. This is true even for the 3 level atom, and this is a general expression which can be derived from the angular momentum algebra. So much for the first postulate. The second postulate is the following. So, there is postulate 2. And this postulate says, with every physical system, there is associated an abstract Hilbert space. Vectors in this space represent states of the system. While I have not introduced the concept of a Hilbert space is a linear vector space on which an inner product has been defined and which also has a concept of completeness. Again, completeness is best described and understood in the context of infinite dimensional spaces, becomes non-trivial there. But as far as the finite dimensional linear vector spaces are concerned, the completeness relation has already been spelled out by me, and completeness is a concept that needs to be understood mainly in the case of infinite dimensional spaces, which I will do subsequently. The spin system that you have seen is certainly, the concept of completeness is pretty much there already. So much for the Hilbert space. In general, any state of the system would be a vector in this space, and a general vector can be written in terms of the basis vectors as superpositions of the basis vectors. So, already there is the concept of basis vectors. I have this space, it is spanned by the basis vectors. So, if it is an n dimensional space, there are n basis vectors. By definition, these are linearly independent vectors, and every vector in the space can be expanded as a superposition of these basis vectors. Now it is very convenient to choose an orthonormal basis where the basis vectors are mutually orthogonal and normalized to unity. The orthonormalization, as I indicated in my last lecture, is done through a procedure called the Gram-Schmidt orthonormalization procedure. And before we proceed, it is good to understand this procedure. So suppose I have a basis set, let me call it phi I is equal to 1 to n, because it is an n dimensional space. Let me start with the first of these basis states. I can always normalize the state to 1. So you consider phi 1, phi 1. Suppose it is not equal to 1, I can always define the ket phi 1 prime, which is phi 1 by phi 1 phi 1 square root, because then phi 1 prime is phi 1 by phi 1 which is equal to 1. So I have normalized one of the basis vectors to unity. So now let me look at the second vector in this set. The second vector is phi 2, and I am given that phi 1 prime is equal to 1. I need to construct from phi 2 a vector which is orthogonal to phi 1. In general, I expand phi 2 as a phi 1 prime plus some other ket chi. I require that phi 1 prime is orthogonal to phi 2. So clearly, from the first term I get this, and from the second term I get this. So this should be equal to 0. But this is 1 because I have already normalized phi 1 prime, and therefore A is equal to the inner product phi 1 prime chi. In other words, phi 2 should be selected to be minus phi 1 prime chi, this inner product, which is in general a complex number, phi 1 prime plus chi. Now we need to normalize phi 2 to unity, and for that, as before, I will divide phi 2 given in this fashion by the square root of the inner product of phi 2 with itself, and therefore phi 2 prime inner product is 1. So I have normalized the new vector, which is phi 2 prime. I therefore have two vectors in this space which are normalized to 1 and which are orthogonal to each other, namely phi 1 prime and phi 2 prime. I have to repeat this procedure with the third vector phi 3, which I expand as b1 phi 1 prime plus b2 phi 2 prime plus some vector lambda. My requirements are the following, that phi 1 prime phi 3 is equal to 0 and phi 2 prime phi 3 is also equal to 0. It is evident that if I first work with phi 1 prime phi 3, that just gives me B 1 plus phi 1 prime lambda, because I have already shown that this inner product is 0, which tells me that B 1 should be equal to the inner product phi 1 prime lambda with a negative sign. Similarly, the fact that phi 2 prime phi 3 is equal to 0 implies from here that B 2 plus phi 2 prime lambda is equal to 0, or B 2 is equal to minus phi 2 prime lambda. Again, I have used the fact that the inner product of phi 1 prime with phi 2 prime is equal to 0. Therefore, I expand phi 3 as minus phi 1 prime lambda phi 1 prime. This is a ket and this is a number, minus phi 2 prime lambda phi 2 prime plus lambda. In this manner, I can proceed and get an orthonormal basis of n basis vectors. By definition, they are linearly independent, and now they are also mutually orthogonal, and each vector is normalized to 1. So much for the Gram-Schmidt procedure. The second postulate clearly said that every vector in the Hilbert space represents a state of the system. So, a general vector in the Hilbert space, which I will call psi, can be expanded as a superposition of the phi's or the phi primes now in this context, because these are the orthonormal bases. I can, without laws of generality, remove the prime and say that I have a set of n mutually orthogonal vectors phi k, which are the basis set, and any vector in that space can be expanded in terms of this basis set. This is the expansion postulate. This is quantum superposition, because I can superpose basis states to produce all vectors in that state. Now, the question is the following. I have operators given by my first postulate which act on states. What kind of basis states can I select? I have already demonstrated in the context of the 2 and 3 level atoms that you could choose different basis states, and these are unitarily related to each other. They are related by a unitary transformation. I have also demonstrated that the Lie algebra is preserved under such a unitary transformation. Suppose I were making a measurement of some physical observable. Let us take the familiar example of S squared, and if it acts on any state in that space, quantum mechanics tells us that the state will collapse to one of the basis states or eigenstates of S squared in this case, with the corresponding eigenvalue, because the measurement outcome is simply going to be one of the eigenvalues of S squared. And therefore, the basis states in this context would be simply the eigenstates of the observable S squared, and a measurement of an arbitrary state will lead post measurement to one of the eigenstates of S squared, with a measurement outcome which is the eigenvalue. I could well make a measurement of Sz as well. Now, if I did that, again the system will collapse to one of the eigenstates of Sz with the corresponding eigenvalue, but the physical state of the system is the same, and therefore, the eigenstate that I have finally post measurement of S squared and Sz must be a common eigenstate of S squared and Sz. In other words, what happens to the system after measurement is this: the system collapses to a state which is a common eigenstate of the various observables that are measured simultaneously, giving corresponding eigenvalues as the measurement output. In this context, one needs to understand that if two operators commute with each other, you can find a complete set of common eigenstates. First of all, one needs to understand what one means by a complete set of eigenvectors of each operator. As I said, a bounded Hermitian operator has a complete set of eigenvectors. Now, to digress a little bit, if you take a Hermitian operator, we can show that eigenvectors of a Hermitian operator or a Hermitian matrix of a Hermitian matrix corresponding to distinctly different eigenvalues are mutually orthogonal. So, the bounded Hermitian operator has a complete set of eigenvectors, and if these eigenvectors correspond to distinctly different eigenvalues, they are mutually orthogonal. This can be seen very simply, because if I have a Hermitian matrix and suppose this is the first eigenvalue equation, where A1 is the eigenvalue and psi 1 is the eigenvector, and I also have another eigenvector satisfying this eigenvalue equation, and the eigenvalues are different from each other, then clearly I can do the following thing. I can find out psi 2 H psi 1. Now, it is clear that if this equation holds, H dagger is the same as H, is A 2 star psi 2. So, if I find out psi 2 H psi 1, that will be psi 2, but from my first equation H psi 1 is A 1 psi 1, and A 1 is a number, but I could have used the second equation, and that just gives me A 2 star I know already I have proved that Hermitian matrices have real eigenvalues, so I can drop the star. And A1 is not equal to A2, implies if this has to be true, psi 2 is orthogonal to psi 1. So, that is how you prove that eigenvectors of a Hermitian matrix corresponding to different eigenvalues are mutually orthogonal. So, now the next part is to show that if I have two such Hermitian operators, let us say S squared and Sz, and they commute with each other, then I should be able to find a complete set of common eigenvectors. This is an example. In general, if AB is equal to BA, that is A and B commute with each other, and if psi is an eigenvector of A with eigenvalue little a, BA psi is equal to AB psi. But I know that A psi pulls out an eigenvalue A, so this object is simply AB psi, and therefore, the state B psi is an eigenstate of A, the operator A, with eigenvalue little a. Now, two cases arise. A could be non-degenerate. In other words, there is not more than one eigenvector corresponding to the eigenvalue A. If at all there is one more, that is linearly dependent on the other eigenvector. So, I consider that case, that is an easy case to consider. So, if the eigenvalue is non-degenerate, it is clear that the new vector B psi is linearly dependent on the vector psi. So, a constant C1 B psi plus C2 psi equal to 0. If there is linear dependence, C1 and C2 not equal to 0, therefore, B psi can be written as minus C2 by C1 psi. This is just a number which I will call B, and therefore, psi is also an eigenstate, that psi is an eigenstate of the operator B with eigenvalue little b, and therefore, I have found a common eigenstate ket psi for the two operators A and B which commute with each other. Now, in the event that there is a degeneracy, you have to work a little bit more. Consider linear combinations of the degenerate eigenvectors and show once more that there is a complete set of common eigenvectors for the two operators that commute. Taking the example that we are familiar with, S squared commutes with Sz, and we know that they have common eigenvectors S squared E and Sz E. There is an eigenvalue equation, and this is simply going to be half into half plus 1 h cross squared, and this is just going to be half h cross. Similarly, S squared on the ground state gives me half into half plus 1 h cross squared g, and Sz g is minus half h cross g. S squared and Sz commute with each other. So, the state collapses to a common eigenstate of these observables. The state itself is a very interesting concept in quantum physics, because in classical physics, if you look at phase space, you simply need to know the value of the generalized coordinate, I call it x, and the generalized momentum p corresponding to x at any instant of time to completely know the state of the system. Then there is the equation of motion. The equation of motion will tell you how exactly you could find the values of x and p at a later time. The state is completely determined. But here the state of the system is described by this ket in an abstract Hilbert space. In order to find out what is the state of the system, we need to first of all know what are the objects that we are measuring. In this context, we need to know that we are looking out for eigenvalues of S square and Sz. So, the dynamical variable becomes important, and then one talks about what is the state of the system post measurement. The third postulate is a very important and interesting postulate about measurement itself. This has to do with eigenvalues and expectation values of operators. So, the postulate basically tells us this. So, this is postulate 3. It is clear what the eigenvalues are. We have already spoken about the eigenvalues being the measurement outcomes. But since every state in the linear vector space or the Hilbert space is a possible state of the physical system, I could in general have a state psi, which is a superposition of the basis states in an n-dimensional linear vector space, and it need not be an eigenstate of the operator A. This is the physical observable I am interested in measuring, and this is the operator corresponding to that physical observable. In that case, one does not have an eigenvalue equation, but one talks of the average or expectation value of A in the state psi. This should be suitably normalized because psi itself may not be normalized to unity, and this has a shorthand notation A is identical to this. So, wherever the state is not an eigenstate of A, it is a different matter that it will collapse to the eigenstate after measurement. The value of the physical observable that I intend to measure is given by this expectation value or the average value, and that is a symbol which denotes it. The denominator has been put in because the state need not in general be normalized to 1. If it is normalized to 1, this of course becomes 1 and the numerator will do. So, let us look at this expectation value in the context of the general state psi. So, I have A psi is summation over k C k A acting on phi k, where phi k are the basis states corresponding to A. It is to be read off like this. There are a set of states phi 1, phi 2 up to phi n. So, I have A phi 1 is A 1 phi 1, A phi 2 is equal to A 2 phi 2, and so on, all the way to k is equal to 1, 2, 3, 4 to n. So, in general, if I take any one of these, the eigenvalue is this, and since this is merely a number and A acts linearly, it just acts on every term in this expansion, and therefore, I have this. But this object is clearly given in the following manner. A on ket psi is summation over k C k, and from these eigenvalue equations, it is clear that this is what I have. Now, you see I need to find psi A psi, that is the numerator. This object is simply equal to summation over L C L star phi L. The ket has become a bra vector. These are numbers, these are coefficients. So, when I take the bra, each coefficient becomes is replaced by its complex conjugate. And since I do not want to confuse indices, I have used L here instead of K, and therefore I sum over L here and I sum over K there. I need to use the fact that this is an orthonormal basis. I can write the orthonormality condition as phi L, phi K inner product is delta L K, where delta L K is a Kronecker delta. It means that when L is equal to K, is equal to 1 say, the answer is 1. Similarly, when L is equal to 2, the answer is 1, and so on. But if L and K are different, the answer is 0. So this is what I have, and these are numbers, so I can well write it in the following manner. I have psi A psi is summation over L and K, that is a double summation, C L star C K A K, the inner product phi L with phi K, and that was a delta L K, which means you can get rid of one of the summations, and I have C K star C K A K. I can well write this as modulus of C K squared A K. And therefore, the expectation value of A is summation over K mod C K squared A K by this. This object is easy to determine. In the event that psi is not normalized to unity, and since psi is expandable in terms of the basis vectors in that fashion, I can find out the inner product psi psi use the fact that there is a delta L K out here, remove one of the summations, there is a number, and therefore I just have summation over K modulus of C K squared. And therefore, the expectation value of A, this average value of A as a measurement outcome, is simply given by summation over K modulus of C K squared A K by summation over K modulus of C K squared. Now, the event that psi is normalized to 1, it is clear that if this is 1, modulus C K squared summation over K is 1, and then it is clear that expectation value of A simply has the numerator. Because the denominator is 1. This has to be properly interpreted. It means the following. Suppose I conduct a number of trials to experimentally determine A, and I find the average value of these trials. The measurement outcome would be one of the eigenvalues of A, which is little a k, could be A1, could be A2, could be A3, it is one of the eigenvalues, with probability modulus of C K squared. Therefore, the eigenvalue A1 will occur with probability, in fact with probability modulus of C1 squared by summation over K modulus of C K squared, but I am assuming that psi is normalized to 1, and then it makes it simpler to explain because A1 will occur with probability mod C1 squared, A2 with probability mod C2 squared, and so on. So, the measurement outcome really occurs with a certain probability. Each of these outcomes is possible with a certain probability, and therefore, this is a weighted average that we have here. This is the sum and substance of the third postulate, which tells us about expectation values as opposed to eigenvalues and measurement outcomes. I will continue to describe this and go on to the other postulates in my next lecture.